Okay, my friends, we're going to pick up where we left off in class, which was talking about chemical bonds, okay? Chemical bonds are the ways in which two different atoms connect to make a molecule. So there are different ways that that can happen. Remember that the electrons are the important elements in this. I probably shouldn't use the word element because are the important structures in this. It's the electrons that bump into each other and that interact with each other to cause the chemical bonds that we'll be talking about. Okay, so there are three main types of chemical bonds that we'll be talking about as we go through this and as we go through the year talking about the chemistry of atoms and molecules. The first type is an ionic bond. Remember, we said an ion is a particle that has a charge, either a plus charge or a minus charge, okay? An ionic bond is achieved when one atom completely gives up an electron to another atom. For example, in this picture, we're looking at sodium and chlorine. If you'll remember, sodium its symbol is Na, and it has an atomic number of 11, which just means it has 11 protons in its nucleus. Each of those 11 protons has a positive charge, so it's in order to balance that, the sodium atom needs to have 11 electrons as well, so that it will have 11 negatives to balance its 11 positives. And so we have, if you'll remember your electron shells, the inner shell can hold 2, the outer shell here can hold 8, which means that accounts for a total of 10, which means we have to have one more electron in this outer shell here to make 11. Now, I want you to think of this electron is like a mosquito buzzing around your head. You just want to kind of get rid of it, and that's maybe, sodium's state at this point. Chlorine, on the other hand, has an atomic number of 17, so it's got 17 protons in its nucleus, and it has to have 17 electrons in its electron cloud to counterbalance that and give it a neutral charge. So here comes, it's 2 plus 8 is 10. And then the outer shell here, it's got 1, 2, 3, 4, 5, 6, 7. So that's a total of 17. But notice it would really like to have that, and please note like in quotations, it really wouldn't like anything, but it will make it more stable if it can get rid of that empty spot in its outer shell. It would like to have 8 electrons in its outer shell if it could. Well, this guy wants to get rid of one, this guy would love to gain one, and so they do. This electron is completely given, just completely handed over to the chlorine atom. Now, since this guy loses an electron, he is now an ion. He has got one more proton than he does electrons, and so that makes him a +1 charge. This guy has one more electron because he has taken this one from sodium, so he has an extra negative charge, so he's a -1. Now, we know that opposite electrical charges attract each other, and so once they have swapped this electron, given this electron over to the chlorine, and they have now got opposite electrical charges, these two guys will just cling together because their opposite electrical charges will attract them to each other. So this is called an ionic bond, made when two ions cling to each other because one ion has given its electron over, or one atom has given its electron over to another, creating two ions, and then their opposite charges cling. It can be, while it's a stable, good bond, it can be easily broken. If you think about water, as salt, for example, all you have to do, which that is what we just created, by the way, salt, NaCl. Just drop it in water and that bond can be pretty easily broken, okay? Oh. Okay, my computer's being annoying, so. All right. Now, the other type of bonds, and this one, if you've got to pick a bond to be important to us in biology, please pick this bond, the covalent bond. In this bond, you've got chemical bonds formed because electrons are shared between atoms, okay? The reason atoms would share electrons is, again, in an effort to fill up that outer electron shell, which, remember, the 8 is the ideal number to have in most outer shells of most atoms. Covalent bonds, when they are created, are very, very strong bonds. So let's look at this diagram down here, for example. In this diagram, we've got a carbon atom, and carbon's atomic number is 6. So that means in this inner shell, we'd have 2, and in this outer shell, we'd have 1, 2, 3, 4 electrons. Hydrogens, on the other hand, have an atomic number of just 1. So if I've got a hydrogen, it's got 1 measly electron in its outer shell. Now, what you see here is this hydrogen has buddied up with this carbon, and as long as they're buddies, the hydrogen here gets to kind of borrow this electron from this carbon, while this carbon here gets to kind of borrow this electron from this hydrogen. And if they stay close together, linked up like this, then hydrogen gets to feel like it's got 2 in its outer shell, and carbon, if it buddies up with 3 more hydrogens in addition, gets to feel like it's got 8 electrons in its outer shell. And these covalent shared electron bonds are very, very strong. That's important for you to remember. And they are found within almost all of the chemicals that are important for living things, okay? Please note that covalent bonds can be single bonds like this, where you share one pair of electrons, or they can be double bonds where 2 atoms actually share 2 pairs of electrons, or they can even be triple bonds where 2 atoms would actually share 3 pairs of electrons. The more bonds you have, like this would be an incredibly strong bond between 2 atoms if 3 electron pairs are being shared, okay? These are all single bonds here, and that's what we'll talk about mostly in our class. Okay, now, another important thing, how do we get these chemical bonds made? Well, usually we have a chemical reaction of some kind. And that's, of course, any process in which we have a chemical change occurring. In a chemical reaction, you start out with one thing, and those things are called your reactants, the things that go into the chemical reaction, and then you get something by the end of it, and that's called your product, whatever results from the chemical reaction. So usually we phrase it in the form of an equation. You'd have your reactants over here, whatever that may be, and you have an arrow pointing over to the right, and then you would have your products shown on this side. So reactants would be here and products over there. All right, now we need to talk in some detail about water, okay? Water, we know, is H2O, and it's 2 hydrogen atoms, which are represented here by these green balls here, covalently bound. Here we see electrons being shared to an oxygen atom, which is shown right here with all of its electrons, okay? So covalent bonds, there's a covalent bond. I'm going to draw a water molecule here. Here's a hydrogen, here's an oxygen. There's a covalent bond right there and a covalent bond right there. So remember, these are strong bonds. They are not easily broken, and this is a very stable molecule, okay? And why are we going to talk about water? Because water, as you probably already know, is uniquely important to life. Life as we know it could not exist without this 2 hydrogens and an oxygen covalently bound together. It's really, really important. Okay, water has unique properties, unique characteristics, if you prefer, that make it absolutely essential for life. We know it covers an enormous amount of the Earth's surface, around 75%, and it is the most abundant thing that's in your body as far as a compound goes. You are basically a great big sack of water. Now, that's really an oversimplification because there's other things in you that without which life would not exist either, but you've got a lot of water in your body. Okay, all right, so what is so unique about water? Why water? Why not something else? Okay, and it boils down really to this atom here, oxygen, and the way it interacts with the hydrogens that are in a water molecule. Oxygen loves electrons, okay? It loves them. In fact, it loves them a little too much. It doesn't like to share them. Because it loves electrons so much, we call the oxygen atom electronegative, which simply means that it loves electrons and does not share nicely. Okay, it is not a good friend on the playground. Oxygen is not, because when you want to share your electrons on the playground, oxygen will say, yeah, let's share. That sounds like a great idea. But it will snatch your electron and it'll let you see it every, 2 or 3 days on when it feels like it. But mostly he's going to keep it to himself. Okay. So when a oxygen atom, which I'm going to draw like that, and hydrogen atoms share electrons, this oxygen guy is going to keep the electrons that these two hydrogens are contributing more to himself, more to his side of the covalent bond. Okay? It's as simple as that. He's not sharing the electrons fairly. He pulls the electrons of the two hydrogen atoms closer to himself. Okay? So therefore, what happens is, because he's keeping the electrons more of the time to himself, he's got a slightly more negative, because remember, electrons are negative, he's got a slightly negative charge to him on this side of this little water molecule. Whereas the hydrogens are having their electrons kind of taken from them a little bit. They're not outright stolen. It's not an ionic bond. It's a covalent bond. They're sharing electrons, but they're not getting to share them equally. And so as a result, they don't have those negative electrons around them very often. So overall, they tend to have kind of a positive charge because they kind of are losing the negative that should be around them most of the time. And so what you end up with is this water molecule is almost like a little tiny magnet, only it's with electrical charge. It's got a plus end and a minus end, kind of like a magnet. If we had a magnet here, you have a north and a south pole and they kind of act differently. Well, we've got a plus and a minus end on this water molecule, okay? The oxygen end is slightly negative. The hydrogen end is slightly positive. And all of this is because oxygen is electronegative. It doesn't play nicely with the electrons. Now, because of that, because it has these opposite ends, we say that water is polar. Okay? Water is polar, meaning it's got two different ends, two different poles, kind of like this magnet might have two different poles. So polarity is when one molecule, like a water molecule, okay, two hydrogens and oxygen, for example, has one end that is different from another. That's polarity. It's got two different poles, okay? And remember, that is happening in this case with water because oxygen is so daggone electronegative. Darn that oxygen. All right? So, oops, I don't want that. All right, so here's a better diagram showing water's polarity than my little chicken scratch. Here you've got the two hydrogens and see that they have a slight positive charge. Why? Because oxygen doesn't play nicely. It pulls their electrons more towards himself, and so he's got a slight negative charge, okay? Now, because water is polar, because it is set up with these opposite ends and almost like a little magnet, okay? The negative end of a water molecule, if this is my oxygen and this is my two hydrogens, the negative end of this is going to tend to be attracted to things that are positive, whereas the positive end of this is going to tend to be attracted to things that are negative because opposites attract, okay? So the negative end, or remember it's the oxygen end, will be attracted to positive particles. The positive end, or the hydrogen ends, will be attracted to negative particles, okay? Now, why have I talked so much about this? Because it is this tendency of water to behave like a little magnet, to be polar. To be polar. Water is polar. It is the quality of water that causes all of its other properties that we're going to talk about to exist. The polarity of water is what makes it so incredibly important for life on Earth and makes it behave in kind of peculiar, very unique ways that no other substance acts like, and makes it so important for life on Earth. Okay? Now, because water is polar, here we go. Let me draw them again. Here's my little oxygen and two hydrogens. Okay? Water molecules tend to be attracted to each other due to the fact that they're both like little magnets. You know, little magnets can be attracted to each other, okay? Now, when little magnets are attracted to each other, though, North Pole and North Pole aren't attracted to each other. It's north and south. Well, when water molecules are attracted to each other, remember the charge at the hydrogen end is a little bit positive. The charge at the oxygen end is a little bit negative. Little positive, little negative here. This little bit of negative is going to be attracted to this little bit of positive here. And so what you tend to get is water molecules, now I'm going to draw these guys over here, water molecules tending to cling together with the negative end of one molecule attracted to the positive end of the other one. Ever so slightly. Let me write that word. Slight. It is not a strong connection, because remember, this is just a slightly negative and a slightly positive charge because oxygen isn't quite sharing nicely, okay? But that slight little attraction is enough to make these guys, these two water molecules, kind of want to cling to each other, okay? Water molecules are attracted to each other due to their polarity. Now, the weak little bond that is created right here, it's not a strong covalent bond, it's just a slight bond, a weak bond, but it's significant. They are called hydrogen bonds. Don't ask me why. I mean, obviously hydrogen is usually involved in them, but this can occur between other things too. But these are called hydrogen bonds. They are weak compared to covalent bonds, but it is stronger than having no attraction at all for each other. It's stronger than no bond at all. And so, because these hydrogen bonds, and let me make sure we get that hydrogen bond right here between two water molecules. And remember, if you had millions of water molecules, they'd all be attracted to each other in this way. It is because of these hydrogen bonds that water acts really uniquely and makes it absolutely critical for life as we know it to exist. It could be that there's life on other worlds, other places, somewhere of which water isn't so critical. But as we understand life, water is really important. And it's because of the hydrogen bonding that water has between itself and other water molecules that makes it so important. Now, you might ask, Mrs. Coleman, why? Why does this fact that water likes to kind of stick to each other, what is the big deal about that? Okay? And I would say that's an excellent question. So what we're going to do is talk about that. First of all, this is a little bit better diagram of hydrogen bonds than my chicken scratching, okay? What this is showing here is a water molecule, oxygen, two hydrogens. Here's another water molecule, oxygen, 2 hydrogens. The little green lines, those are weak hydrogen bonds, okay, that are holding them together. And you can see we've got another hydrogen bond right here between this water molecule and this water molecule. It's negative oxygen attracted to this positive hydrogen. Remember, slightly negative, slightly positive, okay? All the unique properties of water, and we're going to talk about several, there's not just one or two, there's several unique properties of water, are derived from the fact that water is polar. And why is water polar? Basically, water is polar because oxygen, it doesn't share nicely. Oxygen is electronegative. Get that in your head. Oxygen is electronegative. That's one term. But water, because of that, water is polar. Okay, that's an important distinction. Now, I'm going to go through with you several properties, the several properties of water that you need to know. I think there's 7, and I'm going to do that in the second podcast so you can take a break. All right, I will catch you in the next podcast. Sorry, take it easy. See you soon.